Okay, welcome back. This is our first true application of right-angled trigonometry. We should be pretty comfortable now with using sine, cosine, and tangent to navigate around right-angled triangles in order to find either missing lengths or missing angles depending on the situation. Now we're going to be looking at the specific cases of two types of right angles, and they are angles of elevation and angles of depression. These are the angles that we consider in a right-angled triangle when observed from our own eyes, things that are either elevated above a horizontal line or dipping down below a horizontal line. And those in order are respectively are the angles of elevation or depression. It could be that you are standing here on a ledge or on the top of some big hill or something like that, and you notice something even higher above you. So there would be some sort of angle of elevation or angle of tilt that you have to provide to your head or your eyeballs to make direct eye contact with that object. Or perhaps there could be something that's below you. Perhaps you're at one of the bluffs at Brack and you're taking a look down at a boat. That could be something that's lower down, and you would have to work out how much further down something is. Okay, but they're always measured from the horizontal. So you see here, we still have the same words that we associate with the right angle triangles from our last lesson. There's the opposite, adjacent, and hypotenuse side, but the angle of elevation, the angle is here and it's always measured from horizontal. Angle of depression, on the other hand, just taking a little twist on that object here, is exactly the same, just from a different perspective. It remains opposite, adjacent, hypotenuse, and the angle continues to be here, but now it's an angle of depression because it's flipped over. So here's a diagram that probably summarizes it pretty well. Whoops, I went the wrong way on that one. Pardon me. Do that again. And here they are together. But again, both always measured from the horizontal, looking up from horizontal, looking down from horizontal. And those are the angles of elevation and depression respectively. So the reason that we like using this is because we can measure inaccessible angles or inaccessible lengths. Let's take a look here. What just happened to my screen? Okay. Right. Yeah, if you knew some distances around this building, you'd be able to work out what the height of the building was. So here's an actual example. Let's suppose you're at a base of, you're out on the water and you're taking a look. You know that you're 98 meters away from a point directly beneath a point that you're interested in, and you can measure using different tools that this is actually a 38-degree angle. If you knew how far away you were, of course, you can superimpose a right angle triangle over top of it to work out how high it must have been in the first place. To do that, and it's often the case when we're dealing with angles of elevation, angles of depression, we're going to be using the tangent ratio, because very often we're going to be knowing something about the adjacent side and inquiring about the opposite side, or vice versa. Same over here. If you knew how high a perch or a cliff was, or an elevated point up here, you could then work out how far away you were from it if you knew what the angle of elevation or depression is. Now you'll notice that here this angle happens to match this angle down here because of parallel line theory that you would have done when you were younger. So this angle here, it's a Z pattern. It must be the same as this angle down here, and that fulfills the obligation to know the angle inside the triangle. Anyway, so hit pause there and try and work out the values of those variables there. One is H and the other is D, and in a moment I'll present my solution to you. Okay, here you go. I got the height of the cliff being 76.6 meters, and I've got the distance from the cliff in the second scenario with the boat as being 45.1. If you're not sure how I did that, you can see what I've written there in green, or you can ask me. Okay, now here's one where it's a bit more intriguing. You're observing a flagpole of some unknown height that sits perched atop a building whose height itself we don't know. So if we're trying to work out just the height of the flagpole, notice that it's not itself a side of a right angle triangle. However, it participates in a line that is. So if you combine the height of the flagpole with the height of the building, those two together make up a side of a right angle triangle. But later, the building itself also represents the height of the length of a side in a right angle triangle, but a different right angle triangle. One of these triangles has got a 38-degree angle in it, that's that one there, and the other smaller one's got a 36-degree angle there. So what we really want to be doing here is having a new diagram. If you're going to try and work within the structure of the diagram given to you, you're not giving yourself the best chance for success here. All right, let's see what's going to happen here. All right, first thing I'm going to do is I'm going to redraw that triangle. Now, I would have, if I was working on paper like you, I would have redrawn that triangle, which is the height of the flagpole and building combined, and I would have eliminated the information about the 36-degree angle from this diagram. And I would have noticed that A is the height, and we've got an angle of elevation here of 38 degrees, and we have an adjacent side of 200. Now, using that information, I can figure out that A must be 200 times the tan of 38. Again, if you're not sure, you can work out the ratio. A divided by 200 is the tan of 38, and so therefore A must be 156 meters. That comes via your calculator. Secondarily, I'm going to work out just the height of the building, because if I can, I know that this height of 156, which is the flagpole and building combined, I can remove the building, leaving me with just the height of the flagpole. So what do I have now? I redraw a new triangle and I bring back the 36-degree information. 200 remains the same, and I follow along and I see that the building itself must just be 145 meters using tangent principles. And so now all I need to do is find the difference between those last two calculations. In other words, finding out A minus B, and that would be 11 meters. 156 minus 145, or 11. And, you know, if written another way, here's another summary of everything that happened. It actually rounds off to 10.9. Okay, this is probably the most demanding problem, and I think you're going to want to hit pause a couple of times and review what was said or how it was calculated. A helicopter flies horizontally, so on a flat line, at a continuous altitude at 100 kilometers per hour. That h to the minus 1 means per hour. It sort of indicates that it was kilometers divided by hours, which is the conventional unit for speed, but it's just written another way algebraically because it fits nicely in a paragraph. It takes 20 seconds for the helicopter to fly from directly overhead to being at an angle of elevation of 60 degrees. Or this screams out for a diagram. Find out how high the helicopter must be. All right, I'm going to get a diagram going here and see what's happening. So we have a helicopter flying over some person, perhaps that's you, and 20 seconds later, it's moved to a different position, and we would, let's see, if you're flying at 100 kilometers an hour for 20 seconds, that's a distance that we can work out. Let's just think about that. Kilometers per hour, hour is a time unit, and seconds is a time unit. So we got to work out how much of an hour this is. It's pretty small. Whoopsie. So, but we can work out that it's 1/180th of an hour. Why? Because 20 seconds, you would divide it by 60 to turn it into minutes, and then that number would in turn get divided by 60 to turn it into hours. And if you put all that in your calculator, 20 divided by 60, find an answer, divide that by 60, the answer is 1/180, and now you've converted it to hours. But we know from previous learning that if you ever want to have a distance, all you got to do is multiply the speed times the time. They told us the speed, 100 kilometers per hour, and now we've worked out the time in a more convenient format, which is 1/180th of an hour. And if I multiply those two, I get that the distance is 5/9 of a kilometer. If you type in 5/9 in your calculator, it's going to give you a decimal number, a recurring decimal number. I think it's better to leave it as 5/9 because that way you don't have any rounding off errors to consider, because ultimately you're going to have to make a decision how to round that number off for subsequent use. Okay, so here we go. I'm going to sort of redefine the problem. Rather than saying that the helicopter flew for 20 seconds at 100 kilometers an hour, I'm just going to say that it flew 5/9 of a kilometer. Remember, ultimately we're trying to work out how high the helicopter is, so that's over here, but we were told eventually that there's going to be an angle of elevation of 60 degrees. That means from this person's observation, it's 60 degrees looking upward. But because of the Z pattern in geometry, we know that this is also 60 degrees here. And now this is the height of the helicopter, or I could have done it over here, I suppose, doesn't really make any difference, and made this the height of the helicopter and used this 60 degrees here, and the 5/9 that's here would have also matched the 5/9 that's down here. Either way, you got a nice little trigonometry problem here, and like before, this is going to be the opposite and the adjacent. So this is a tangent question. Move that over there. And the tangent is h over 5/9. Rearranging algebraically, we get that the calculator must be 0.962 kilometers high. And that's pretty specific. It's not measurable because the diagram is not to scale. And that's how we solve that problem. And, angles of elevation and angles of depression. Okay, it's time for you to practice some of these now. We can do some of these in class. We can do them outside of class, whatever you like. You can take a look at these here. Let's see what questions we got. Worded problems for sure. They all scream out for diagrams. There's your problem set 1, 2. So we're in exercise 1I. There's I, and there's the questions you're responsible for. Okay, good luck. I'm here to help you. Do your best.